In our last section of notes, we looked at the idea of a sampling distribution and looked at some of its characteristics. Now we're really going to focus in on one specific type of sampling distribution, which is a sampling distribution for p-hat. So that means for sample proportions. And what we're interested in when we look at sampling distributions is we're going to be interested in the shape, center, and spread. So here's one set of sampling distributions. In this one, the p-value, or the proportion of orange candies, is about 45%. And we're taking samples of size 25, 400 times, and we've made a dot plot with 400 dots on it. We do here basically the same thing, but this time now we're doing a sample of size 50. And really what you can see here is both of these end up having a mean close to our p-hat value, but the standard deviations are a little different. The standard deviation for the larger sample size is smaller, and that's consistent with what we've seen in some of our previous sections of notes. Now here's two new sampling distributions where we changed the probability of getting an orange candy to 0.15. Now you can see both of these distributions are centered at 0.15, and again, the one with the larger sampling size has the smaller variability in the distribution. So just to kind of summarize what we saw here, not always, and we'll look at when this happens, but sometimes we will end up with something that is normally distributed. That's definitely not always the case for proportions. Again, I'm going to give you kind of a condition that you'll need to check in order for that to be true. But sometimes it looks like a normal curve for the shape. For center, this happened in all four distributions that we looked at, where our sampling distribution had the same mean as the population. That's always going to be true. They're going to be close to each other. And for variability, we saw that same pattern both times and in previous sections of notes, where as you take a bigger sample size, your variability gets smaller. Now, in terms of figuring out what your p-hat is, you're just going to be taking a sample. Let's say you took a sample of 50 pieces of candy, and then X would be the number that you got that were orange. So maybe you'd have like 40 out of 50, and then that would be your p-hat for the proportion of oranges in your sample. So now what we're looking at is we're looking at something similar to our binomial random variable from the previous unit, where we said that you take your number of successes, your number of trials times your probability of success, and that gives you your mean, and you also have a formula for your standard deviation. Now for our p-hats, we're taking the number of successes divided by the total number. So what that does is it essentially just ends up canceling out the n's, the 1 over n and the n, multiply to 1, so you just get p. So that's why our mu sub p-hat ends up being p. And we have some similar canceling out that goes on in our standard deviation formula. So on your formula sheet, you don't need to memorize any of this, but this formula, mu sub p-hat equals p, and sigma sub p-hat equals the square root of p times 1 minus p over n, all inside of the square root. Those are both on your formula sheet. You're just kind of seeing where they're coming from here. So a couple of things to be on the lookout for. This is just kind of summarizing what we've got. We're taking a sample of lowercase n from a population of size capital N. We've got p equaling the true probability of success for the whole population, and then our p-hat is what happened in our sample, what proportion of those were successful. One thing, remember from back in chapter 6, we said that we can only use the standard deviation formula if we are having samples that are taken independently, which means we're doing them with replacement. Now, since that never happens, we never really take samples without replacement. We have to check our 10% condition, so that's the same as it was back in chapter 6. But here's what's new. So we had said that the shape is approximately normal sometimes, but not all the time. So what you need to do is you need to check what's called the large counts condition. And in order for the sampling distribution of p hat to end up being approximately normal, you need to do n times p, so the number of trials times the probability of success, and n times 1 minus p, so the number of trials times the probability of failure, and both of those values must end up being greater than or equal to 10. If that is true, then your sampling distribution will be approximately normally distributed. Please take a few moments to try the practice problems before moving on to the next section of notes.